Hello, I'm Hannah Wagner, and in this lab we studied the motion of a pushed object. Our goal was to compare our data taken from a real moving object to our hypothetical data from a computational model to determine the accuracy of our model. The results showed that the constant velocity model closely matched the experimental data, but slight concavity revealed the presence of friction. Our purpose in completing this lab was to analyze the accuracy of our computational model's predictions of displacement over time using constant velocity compared to real data to understand the differences between theory and reality. To collect data from this lab, we placed a meter stick and a marker on the table and then recorded as we gave the marker a small push from above. The meter stick allowed us to analyze the motion in the video and precisely know how far the marker traveled in each time step. I was able to determine the distance with help from the tracker software that allowed me to use consistent time steps and measure the distance the marker rolled. I based my model on Newton's first law of motion. Objects in motion stay in motion unless acted on by an opposing force. My code calculates displacement with the equation shown where x is displacement, v0 is initial velocity, and t is time. In the code we applied the momentum principle, but since the net force is equal to 0, the final initial velocities are the same, indicating no acceleration. We assumed constant velocity because after the initial push, no significant forces were expected to act on the object. The system in this lab is the object being rolled, and the surroundings are the table and air. The initial position is at the origin, and the initial velocity is 0.2215 meters per second in the positive x direction. This velocity was obtained by finding the average velocity from our video by dividing the distance the marker traveled by the time it took. For my code, I use a time step of 0.01 seconds to calculate the change in position. I created a calculation loop of 2.6 seconds to match my experimental time and then set the net force equal to 0. This causes the velocity to remain constant despite the velocity update equation being written into the code. The position is then updated using the shown equation. Since velocity is the distance over time and we are multiplying it by our time step of 0.01, we get the distance traveled in that step. The loop then continues appending the distances at each time step until the time reaches 2.6 seconds. This graph depicts the position of the rolled object versus time for the computational model and the actual measured data. The strong linearity of the graph confirms the constant velocity motion because a linear relationship in a position versus time graph indicates no net force. The two lines are very close, indicating a high accuracy of the computational model. However, there's a slight downwards concavity that indicates a force opposing the motion that is present in the actual data and not in the computational model. Since acceleration is the second derivative of position with respect to time, concavity in the graph indicates a non-zero acceleration. Our model does not account for any friction opposing the motion, but in reality this is not the case. The concavity of the data can be explained by an acceleration in the negative x direction causing the position of the object to increase at a decreasing rate. There could have also been small measurement errors or an uneven surface causing some of these discrepancies. If we included friction in the model, then the net force would not have been equal to 0 and we would see a negative acceleration as previously explained, making the model more accurate to real life. If the initial velocity were larger, the slope of the position versus time graph would increase as the slope of the graph represents the change in position over time, or the velocity. Overall, the constant velocity model is a mostly accurate predictor of the motion of a rolling object after being pushed. The mostly linear position versus time graph confirms a near zero acceleration as theorized by Newton's first law. However, the slight negative acceleration can be explained by the absence of friction in the model.